plan. So the first lecture, this lecture will be about quantum spectra, definitions and conjectures. So it will be mostly speculative. So the next talk will be about tomorrow blow-up without convergence, and the third lecture will be applications. Yeah, so what I'll talk about is something which have roots from maybe from 95, 96, very old, kind of early days of symmetry, and something which could be done long time ago. And so what we will see is that quantum multiplication and so on has much deeper relations with algebraic geometry, just counting how many curves. It's really related to many, essentially all questions in algebraic geometry in one way or to another. And I'll speak about Gromov-Witten theory, not Foucault categories at all. And Gromov-Witten theory, especially I'll speak about even about genus zero case. And there are some reasons. And this Gromov-Witten theory, there are actually two theories. One is C-infinity theory, or let's say about symplectic manifolds, and another theory is algebraic geometry. Of course, there is some common part between symplectic geometry and algebraic geometry. You have Keller varieties, complex algebraic varieties, but these are really two different things. And symplectic I'll really put in parentheses because Gromov-Witten invariants, people say that they're invariants of symplectic manifold. But if you count how many curves of different genus pass through such different degree pass through such cycles, it's not invariant of symplectic manifolds. It doesn't change if you continuously change symplectic structure. So it's invariant of connected components with specific symplectic structures. Yeah, so it's not really, and symplectic geometry appears only in the way how we count make geometric series. Yeah, so what Gromov-Witten theory? So I'll first describe C-infinity theory. First, C-infinity theory, and where it starts and where it goes. So input we get let's see, C-infinity manifold, compact C-infinity manifold of even dimension, and J is the almost complex structure. So Tame means that there exists a symplectic form such that omega of V which JV is positive for any non-zero tangent vector. And just to guarantee kind of finiteness of some modulus spaces, compactness of modulus spaces. And so the symplectic form is not part of the structure. And the output is GB invariants, which will be kind of like virtual fundamental classes of modulus space of stable maps. So G will be genus and will be number of mark points. B will be homology class. It will be just integral homology class. In fact, if you are just in spheres, genus zero will maybe an element of pi 2, and then it belongs to H2 of something. You can put x to power n, and if you can fairly predict this if you can also add mj bar, or can omit it, and this coefficients in q bar, in q. Yeah, so get not integer class but rational classes, and I will speak about only genus zero part. I will speak about only genus zero part, and so I'll just use some notation. If I have some elements p bar n in cohomology of x, with rational coefficients. And I have this degree beta of my curve. Then I get a number which is get rational number, which is equal to integral of the fundamental class of n. Now, from now on, my genus is always 0, and I take product from all endpoints, evaluation, pull back my evaluation map of classes pi, and get certain number. So I get a map from homology of x q, 10 to the power n to q. Okay. So I get this thing, and they satisfy a long list of axioms or properties. I'll speak about only genus 0, and in fact, recently I've seen somebody wrote a paper that finally he proved, this person proved our axiomatic for high genus cases in symplectic geometry. So it's supposed to be not settled yet, but in genus 0 it was settled. Yeah, so you got many properties, like you get symmetry, under action of symmetry group, and then you get support. These things are vanished for kind of wrong classes beta. It's non-vanishing. It implies that either two things, either beta is equal to 0 or integral over beta of symplectic class is strictly positive. You get non-constant maps. Yeah, so you get this axiom. Then you get something for constant, not as a map, but constant as element 1 in H0 of X. Formula, namely, if you consider correlator 1x, phi2, blah, blah, phi n, with beta, non-zero, then it's equal to 0. If you consider non-constant maps, you get this property. Then you get divisor axiom. Like divisor axiom, that if you consider the class of again form, and two form, and beta is integral of omega beta and this correlator. Then you get dimension. Think, namely, that this integral non-vanish if and only if that sum of degrees of forms this should be equal to some even number, the capital N minus 3 plus n plus integral first chain plus eta, and then you finally get WDVV equations. That's the most interesting part. I hope everybody knows, but just recall if you fix beta, phi1, phi2, phi3, phi4, and then other phi5. And then what happens? You decompose beta in sum of two classes. Decompose a set of the rest into union of two subsets, disjoint union of two subsets, and take the following things. You consider correlator of phi1, phi2, phi I, take product in I prime, then I take delta I, multiply by delta I, 4, get these things. Here delta I are dual bases of cohomology with respect to Poincare pairing. We make sum of such things is invariant under permutation exchange of phi2 and phi3. So that's the most interesting identity. And the usual picture is that you consider we count degenerate curves on which points 1, 2, 3, 4 distributed to different ways and other points sitting somewhere. And here's this intersection point you put diagonal on a manifold which you split using a dual basis. Yeah, so that's all list of properties which we know a priori, and then someone can make generating series. F0. Namely, what you do, you take sum of all n, 1 over n factorial, then take sum over I n, I use my basis, sum of integers, and what you do, you make this all possible intersection numbers which you have, and then you should multiply by a certain weight. You take product over ti, take product by Qii1, Qin, and then we should count degree somehow. So to count degree, of course, one can use this simple Q to power, oops, some things are not working. Q to power beta, which will be element of the group ring. Yeah, so we get kind of group ring, and where it belongs to. You see that second homology of X is a finitely generated abelian group. So what we do? We just identify. So we split this group as some torsion part plus a free abelian group of rank which is second Betti number of X. And when I consider group ring of this group, it will be group ring of finite group and series in several variables. And for finite group, what you should do Fourier transform. So let's just choose some map capital B from H to torsion to U mod Z. And also choose some classes, omega 1, omega up to second Betti number, which will be symplectic forms, such that the homology classes belong to the image of integer homology, and they form a basis of H2 X mod Q. Yeah, so you get many things, and now you replace this Q to power D by more concrete Q to power D, replaced by just over 6, namely we take exponent of 2 pi to 1 be applied to torsion part of beta, so get some root of 1 and multiply by product from 1 to b2 ui to integral omega I beta, and this will be non-negative integers. In fact, it will be positive integers plus 2 z, not constant. Okay, so I get series. So this dependence on torsion can be said that we have not just one series but many series depending on class B, and we get F0 which is invariant of your manifold plus this class B, and it will be looking in some cycloatomic field, because you should get some root of 1, which is denoted just by k. It could be q or q root of 1. And it will be series in variables E1 up to total dimension of cohomology of x with rational coefficients. And also variables q, which goes up to dimension of second cohomology with rational coefficients. So you see the second cohomology appears kind of twice. The t and q appears twice, and in fact, this ti for kind of generators of degree 2 are redundant. So one can kind of forget about them. So they kind of behave like logarithm of q. And so we get some obvious differential equations saying that q dq du dt is the same. Okay, so one can remove this redundant variables. You get all variables except h2 will be t, and for h2 will be q. And then one get sorry?
What is redundant? What is
t are redundant.
Because
yeah. So what is going on? One can get a quantum product. Now maybe I just dirty. It's mapped from cohomology of x with rational coefficients, cohomology of x with rational coefficients, to cohomology of x with rational coefficients, and multiplied by this series of cycloatomic field A. Here this point D. Not equal to 2. Sorry. Okay, so get this series is this multiplication with many coefficients, and we define the product just for two base elements as a third derivative, and we use dual basis. Here the dual base element. So you get the tensor product which depends on these parameters. It's a product from cohomology, depends on this parameter. And so just a way to, there's really no loss of information from going from M0 to this quantum product if you know Poincare duality, so it's essentially the same information. And then what I should give, it gives you a quantum connection on what? On a trivialized bundle. So bundle will be on which base manifold? The base manifold will be spectrum of algebra formal power series in my variables t and q. But then I also multiply by spectrum not formal of just polynomials in one variable with mu, which I denote by u. So get extra coordinate. And fiber is, because the trivialized bundle, is cohomology of x. And how the connection look like? So that's the main formula. In the early days. Namely, along this new variable, covariant derivative with respect to transition of the variable will be this trivial connection plus 1 over u squared times k plus 1 over u times g. So it will be matrices, and with respect to dti or qi or dqi, it will be dti or respectively qi dqi plus 1 over u ai. And ai, kg, and ai are endomorphism of vector space of homology depending on parameters in T. Yeah, there are certain three types of operators. And what are these operators? So these operators are the following one. So the operator K is, oops. It's a really operator K is quantum multiplication by the following guy. You can see the first Chern class of a tangent bundle, so like canonical class, plus certain correction. Some of I such a degree of delta I is not equal to 2. Take degree of delta I minus 2 over 2, I delta I, and consider terms of quantum multiplication by this guy. AI is quantum multiplication by our basis element, and G is constant. It doesn't depend on any on the deformation. G is kind of direct sum, kind of scalar operators acting on each degree in cohomology, E minus n over 2, and to take identity operator of HIX. So you get kind of log diagonal matrix, which essentially gives dimensions.
This formula works even if you have odd cohomology?
Yes. My variables should be super variables, it should be super manifold, super bundle, and so on. So the formula works perfectly okay. So you get this thin connection, and this is flat connection. So the condition of flatness includes all various grading and WDV equations. And now we start ask questions. So this conjectures which I have in C infinity case. First conjecture is convergence. It doesn't matter. Quantum interpretation of zero convergent over a series in complex numbers. Of course, one can ask about periodic convergence for T and U small enough. Yeah, that's a very basic conjecture, and there's really, to my knowledge, nobody really worked on it. It's a very fundamental conjecture. I think it's very difficult, and it would be great if somebody eventually will solve it. Of course, you understand, we in the mirror seem to have many interesting things to do, and this looks like a boring analytic fact. But yeah, we have a wonderful identity. This is just kind of stupid inequality, which you can see through in any example. But the question is how to find general argument to it. And I have a kind of suggestion how to attack this problem, because it looks hard. The idea is the following: the Gromov-Witten invariants are coming from a kind of perfect structure series. So the locally looks like intersection of some two infinite-dimensional submanifolds and some another infinite-dimensional manifold. So you get somewhere kind of like intersection, and we count how many intersection numbers. Intersection could be very, very non-transversal, kind of, and you try to deform generically. Yeah, so we should kind of bound a number of intersection points, and if you can try to think in finite dimensional situation, it's better how to make bounds on this thing. You should kind of smoothly replace these delta functions by kind of like something a bit smooth things, and now I should go to some integral. So it should really go through some path integral. And path integral, I think it should be, if you consider something like map psi of whatever your surface to your manifold. In string theory, integrate integral square, but I think here should maybe add integral second derivative to make it things really regular, to avoid a kind of bad more derivative here to get more and more smooth things. And the idea just to replace by some kind of passing really infinite dimensional integral, so will be the identity is rational number equal to some infinite dimensional integral, and then integral will kind of like pointwise bound, and then one should get into the to the equation. Yeah. But it's really serious issue, this convergence story. Yeah, so it will be one point. And then there are two other conjectures. Which are bad. So the second conjecture said that it's assuming first conjecture. First conjecture says the following: pick Q and T in domain of convergence. To be actual, and any only even variables, and odd variables will be some exterior algebra, so don't worry about it. So I get actual operators. I get actual matrices K and G. Then I get this my connection. And the conjecture that if you go over formal power series in formal Laurent series in U, this connection is isomorphic to some of the following D modules. We take interpret as the D module. You consider U alpha, sum of Z alpha divided by U times the regular D module. Finite sum. So it's some of things which have solution like growing like exponent constant over U. And these constants are, this will be my spectrum. This Zi I know a priori. This Zi is actually spectrum of operator K for given T and Q. And
so the statement is that this is a canonical splitting?
What's the splitting? Actually, this splitting is canonical. It follows from theory of formal differential equations. It's level routine decomposition. And then there is another conjecture.
Sorry, what's the conjecture in this case? Sorry.
No, conjecture is that this pairs of matrices are such that this D module is of form power series is some of exponent. It's pretty formal algebraic statement.
What's the statement?
The conjecture is that in the area of convergence, my matrices K and T, which are complex valued matrices, are such that this connection of form power series is direct sum of exponential terms. Okay. It's some property of pairs of matrices which neither the risky closed, neither the risky open. It's some constructible, complicated constructible property of pairs of. Okay, I can repeat it.
What is written for form of power series doesn't matter.
No, form power series, not every such thing is equivalent to direct sum. There are counterexamples, yeah. One can have solution going like a 1 over square root. When
It's not.
okay,
You do not have rational power. Okay, you do not go to the.
yeah, there's no more complicated guys here. It's.
Can you explain to the rest of us what just happened? So the statement is in general, there is such a decomposition, but with terms that can have powers of u, right?
Here you get 1 over square root of u.
Okay.
And here will be still regular demodus, yeah. But
Okay. And the statement is here, you don't need to take powers of square.
no. At the exponent you get only u2 inverse powers, nothing else. Yeah, it's a real algebraic property of pairs of matrices. And there is this third conjecture. It's about gamma lattice. It's again assuming first and second. One can formulate. I will not bother with the exact definition. One can using values of Taylor expansion of gamma function. Crazy class. Multiplicative cryptic class applies a cotangent bundle to this somehow lattice and make a prediction as we get certain lattice for the differential equation invariant and monodromy, and this conjecture, this gamma lattice is compatible with Stokes filtration coming from this differential equation. Yeah, so it's strange thing. In fact, this 2 and 3, it's more convenient to formulate using Fourier transform. Sorry?
It's lattice of what?
The story is the following. In cohomology of manifolds, there is certain lattice image of topological case theory, and this image will be should be put. It's covariant of this connection u equal infinity, and then approach to 0, then it will be compatible with Stokes filtration.
The conjecture is there exists a lattice.
No. There is a description. There is a description of a lattice
In terms of this data.
in terms of topology of manifold of Chern classes. It's called gamma. Using gamma class, we can produce certain covariantly constant lattice for this equation, and the conjecture it's near 0. It behaves well with respect to Stokes filtration. The formulas are pretty ugly. It's kind of complicated, I don't write them. We'll make Fourier transform. So, like, essentially integrate something like u.
I thought the conjectures only give an asymptotic expansion of what the lattice should be. They don't
No, it fixes your lattice completely. Yeah, I'll tell you just what is going on. We can make Fourier transform go to kind of new variable z. Instead of u, you get new variable ops. Instead of u, you get new variable z, and the connections look like this. So, derivative with respect to dz will be dz plus g plus mu. I'll explain what is mu in a second. D minus q inverse. And derivative of dti. And the same as q dq will be g plus mu ai inverse. And mu is just a sufficiently large integer. In real case, it's sufficient. Mu will be bigger than dimension of x n over 2. Sufficient in our case. All this for large nu, all these connections are equivalent, and we get again flat connection, which will be a bit meromorphic, and conjecture 2 is equivalent to the fact that this connection has regular singularity. And lattice 3 one can also describe in some way. But here we can easily automatically see the singularity of the things will be eigenvalues of operator K, when this matrix will be not determined. So you get some kind of collection of complex numbers moving when you change your parameters Qt and your Frobenius manifold. some kind of basic example. If you take projective space, then the things will be vertices of a regular polygon. And if you get variety of general type, you get just one point, independent of this parameter. Yeah, so it's kind of distinguish Fano and general type in very dramatic way. Okay, one can make some certain enhancement of this conjecture 3 about gamma lattice, which is does really follow from differential equations. And I will call it topological semi-orthogonal decomposition. SOD, it's semi-orthogonal decomposition. So what do we have? We have a topological K0 of x, which is K0 of x plus K1 of x. By both periodicity, you have only two different groups, and these are finitely generated groups, and the total rank is like all cohomology of x. It's rationally the same as cohomology of x. And this thing carries on this group, we have a non-symmetric pairing. In pairing, it's kind of Euler pairing. If your manifold will be complex manifold to reflect Euler-Christie effects, and just write on K0, if you have two complex vector bundles, E and F, what will be pairing between the Chern classes, because it extends just linearity, it will be index of not Chern classes, the classes in K0. So Chern classes, it's if you compare it to homology. You have two vector bundles, it will be index of the following operator. You consider gamma of x e dual times f times even d-bar forms next to the same as odd d-bar forms, and the operator will be d-bar plus d-bar star. It doesn't matter that d-bar square is equal to 0, it gets still elliptic operator, so get kind of index of Dirac operator. Yeah, so this is this pairing, and what is going on? What goes on? We have our spectrum, this quantum application, and choose collection of kind of disjoint path going from minus infinity to my point in the spectrum, some point of convergence. Then if you have such a thing, a situation.
Sorry, what's the variable in this plane?
Sorry?
What is the variable in this plane?
Z. It's the plane, and these are where the spectrum lives. If I draw a collection of paths, then I should get a semi-orthogonal decomposition of my group. K top x will be ordered sum from 1 to number of these points Z alpha of corresponding pieces, and Euler characteristic from Ki, Kj should be 0 for any element. If I less than j, should be semi-orthogonal decomposition. So my form, non-symmetric form, will be block upper triangular, and on such guys acts as the section of braid group. And if you change the collection of paths to another, it's called Gabriel basis, it will be the same action of braid group. But moreover, here you get kind of projection, because if you have decomposition, you get kind of idempotence projector to KPI, and projectors should be lifted, should be given by kernels using this pairing, which belongs to K0 of x cross x. Okay, yeah, so it will be kind of more delicate story, because and K0 can have some torsion, and the torsion equation cannot seem differential equations at all. Yeah, so it will be extra story from which doesn't follow from the connection, and yeah, so that's essentially if I will mention Foucault categories, everything which you can tell about the story. And
sorry, Maxim, can you say a bit more about how the decomposition comes from the paths? Like, how is there a method to explain? What is the relation between the semi-orthogonal decomposition and the paths? How do you define
any selection of paths should give a semi-orthogonal decomposition.
But how?
Somehow. Okay. That's conjecture. Yeah. For example, consider something like cohomology of, if you have Landau-Gisborne model, then you get this corresponding something which maps to the plane Z, and you consider pullback of this path relative to the infinity.
So the intuition is through mirror symmetry.
Intuition through mirror symmetry,
okay, because there's not like an explicit.
Yeah, but they don't use any other Landau-Gisborne model. Yeah. So that's essentially all three problems, and this is topological extensions, and I don't expect any progress soon. Yeah, so it's really it's not even clear how to attack this. See? Okay, so that's all about C infinity version, and now we go to algebraic story, because I said it has this algebraic geometry. And the story is it's an algebraic geometry. We start with, now F will be arbitrary field. Could be finite field, U, C, whatever you want. And then there is still story of, instead of this almost complex manifold, I get X will be smooth proper variety. And such that there exists temporal line bundle, and this is what people call projective varieties, but I don't fix this projective line bundle, so it's the same story. So it will be adjective, not a part of the data. And then there was a story developed by some lady called Flavia Poma. She left mathematics. She now works in City in London, I suppose. But around that time she wrote the thesis. He constructed this Gromov-Witten theory and checked all semantics, especially in genus 0. And Gromov-Witten invariants are elements with which are fundamental classes. Beta, virtual, are now not homology classes but elements on a Chern group in appropriate degree of x power n. And you can multiply mj in bar in with rational coefficients. So these are Chern groups. It cycles up to rational equivalence, and these are really huge things. They could be uncountably generators, and we have not very good understanding what is going on here. So it's much more delicate invariant. But there is a question where I put homology class beta. And here's again obvious answer. You consider first Chern group of X, you make extension to a bar, and mod out by algebraic equivalence. You consider like continuous families of curves. You shouldn't change this class. It's not a second homology, it could be countably generated. Yeah, so you get much more finer story in algebraic geometry everywhere.
So when you talked about the infinity case, you made the point of saying it's an invariant of the component of pi.
Component of pi, yeah.
But in this case, since you've
component just of x only, not component.
No invariance.
No, if x depends on the family, these things kind of arise in the family. Numerical kind of integer rational numbers eventually will be the same, but this will be really for individual manifold. And how to make generating series? Yeah, so here we get really huge things. But this set of albetas, you can map reasonably to Q mod Z when you have a bundle Azumai algebra of X. When you have Azumai algebra of X, when you restrict to a curve, this invariant will be element of Q mod Z. Yeah, so this torsion part of B is naturally captured in the algebras, but also you can map to Z, maybe several times. You just put ample line bundles and consider degrees of ample line bundles. Yeah, so we can make geometric series Q to power B. So we have Q to power B to be kind of understood how to arrange some roots of 1 and maybe some powers of Q, but what to do with variables T? Variables T, it's something which you need some cohomology. I didn't speak about cohomology here. It's Chern groups. No? There are many cohomology series, like Elatic cohomology, crystalline. I don't want to choose any. And I prefer really not to choose cohomology theory at all. Because at the end of the day, all story about complex numbers and cohomology usually some Elatic numbers, so it would be kind of unhealthy to relate one to another. Yeah, so I try to formulate anything without specifying cohomology. So what is the language here? We have this Chern ring, and maybe one can just use abstract operand. Chern operand associated to manifold X will be Chern groups of X n to power X, and we consider all n linear operations replaced by Chern groups multiplied by rational coefficients, and maybe make extension of field. Yeah, so it starts a little bit complicated because Galois group acts also on beta. So here it's probably better to go to algebraic closure and consider this operative section of Galois group. Yeah, and that will be just abstract operand, and all identities will be this abstract operand. Okay, now what about convergence conjecture? Convergence conjecture, one can formulate it pretty easily because we get elements of Chern ring, and one should define some kind of norm on Chern group, on Chern x to power n. Namely, if you get some pluses, some kind of alphas, alpha rational numbers, and some effective cycles, and you find norm of these things, it's something which, by maybe semi-norms, it should be smaller than sum of I, absolute value of I, times degree of the cycle with respect to your choosing ample plus. So it will be positive number. But you get something like whatever one norm and conjecture that it will have exponential growth. Yeah. So you don't just talk about cohomology theory at all, and so that's again conjecture about exponential growth, and it's kind of version of the things we should talk about functional interval, but it should be inside algebraic geometry or finite field. I don't know. It's also another question how to prove it, this boundary. I think it should be easier than C-infinity case. But, this story. Now, when we want to formulate this moving spectrum in this path, we should calculate spectrum of this operator K.
So this means that these put restrictions on where these eigenvalues can be.
No. It means that we can get some actual complex numbers. Yeah. Here, how to calculate spectrum of K, assuming the convergence. Yeah. I have really no idea how to speak about gamma lattice in this framework.
Can I ask some very stupid questions? So the spectrum changes.
Yeah, it depends on parameters. Yeah, spectrum, and for some those who some discriminant will have smaller elements of spectrum, but generally will be certain number of elements of the spectrum which play important role.
So, like for example, for that conjecture, there's for every parameter you get.
For every parameter, you get when things collapse, you get kind of rougher semi-orthogonal decomposition. Yeah. I should have spectrum of K, and this should be in the complex numbers, not in some periodic fields. How to do it? The idea is just I have coordinates on my Frobenius manifold, and let's move only in directions of only algebraic cycles. So we don't go to generic point of Frobenius manifold, just kind of certain linear subspace.
So what's the base of the Frobenius manifold in this object?
Yeah, I don't say anything about Frobenius manifold because I don't want to speak about homology. It will be elliptic things. I don't want this elliptic.
Okay, so this board is about the C infinity case, or is it?
No. It's kind of intuition. Yeah.
Right.
Imagine my field is embedded in complex numbers,
Okay.
but the story will be applicable to positive numbers. The idea is a smooth direction of algebraic cycles.
You don't assume about conjecture.
Sir?
You don't want to assume about conjecture.
No. I don't want to assume anything. There is actually something very funny here, very delicate point. About the Chern groups, when we use mine and wrote paper, we also have these things as Chern groups. But when I try to define this very big generality, maybe in this operator, to have this connection, then you need this operator G for grading. And operator for G for grading, it's what's called cumulative decomposition of a diagonal manifold, which things which is not known, it could be not true. Yeah, so it means that one should kind of it's really interesting. This is deep question of geometry whether one can make this position. But regardless of this, so what does it mean? Moving in direction of algebraic cycles. So we get if you have some homology, then we have image of actual group of X in whatever homology we have. But this image should be something like Chern groups divided by numerical equivalence. It should be finitely generated lattice. Crazy model. It will be realizes of finite type, and then one can kind of assume that variables associated to the things are complex numbers. And so it will be a lattice of certain rank Zm, where M will be something between 0 and dimension of even homology. So how many algebraic cycles you have in your variety? It could be one or another. And so we use only variables associated only to these cycles, and what we get characteristic polynomials of K. It's actually a series with rational coefficients. So if you use this things out of algebra, maybe cyclotron fields, and these variables, this Q in K will be only capital M variables. You get restricted number of variables, and you get series with rational coefficients because at the end of the day there will be some intersection, some complicated combination of usual intersection numbers, which are integer rational numbers. And then this abstract convergent condition says that you get actual characteristic polynomials depending on small parameters, it's conversion, and then you can speak about paths as well. And now it's kind of the big conjecture, kind of categorical SUD, that if you choose this Gabrielov path, then you should get a semi-orthogonal decomposition of derived category of my variety of my field when we start with. Yeah, and these things will work in positive cohesive with there's no Foucault categories at all present. So it means we get some categories C1 or C number is A, and again our home from smaller to another is 0. Yeah, in the common ground, when you get Kelly manifold, it will be compatible with topological question. Yeah, but it's really different question. And yeah, that's again for some future. I have absolutely no idea how to attack it, and maybe even not in our lifetime, I'm afraid. Yes, it's really, it looks kind of extremely difficult, deep question about where we get this. So this kind of good news here that these convergent issues, which are kind of advertised twice here in the infinite algebraic case, are not really relevant. One can formally test it without convergent. Without convergence, everything makes sense. This is Gabrielov path and so on. You get certain series in my variables. And now substituting Q, you substitute by some series you consider series like with rational coefficients in some big variable t, which goes to 0. You can assume that it's kind of, you can try to think it's a very small positive number. You substitute it here, you get a polynomial which roots are very close to r or 0 adequately. You can make Laurent expansions, and roots will be spectrum will be series in Q bar. But Q bar is part of complex numbers, so you get series and depending on small parameters, and what they really look like, you get kind of maybe they go to several shapes and kind of leading coefficients. Then in each coefficient you get some smaller things, and the position of these roots will be roots of some equations with rational coefficients, with some algebraic numbers. One can speak about paths connecting them. Yeah, so that's even it's not convergent. One can speak about this torsor of break group, and then well, this is categorical semi-orthogonal equation makes perfect sense without any assumption. Yeah, so how the things could happen? When you get the semi-orthogonal decomposition, you get a lot of, again, end of functors projected to the individual pieces, which given by certain kernels. And this end of functors given by some complexes on the square of your manifold. So you should get just bunch, using this picture, you should construct a bunch of complexes of vector bundles on my manifold, or dB of coherent sheaf on square of my manifold. And but what I do is I use this only Gromov-Witten invariants, essentially 2 points. Yeah, so you should consider like M02 with different betas. And somehow, but using only finitely many of them, I should combine them to the center functors. How two things could work universally, but again, I have very little idea because in a modulus space of curves you get the stabilizers and it's rational coefficients, but at the end of the day you get things with integer coefficients. That's kind of big mystery. Yeah, so you see that that's the conjecture, which was in some form was really proposed a very long time ago in kind of second part of 90s. But it makes sense. It kind of in positive characteristic when this our conferences has nothing to say about. Yeah, and this towards C infinity and algebraic gives kind of completely different perspective. For example, one can ask about the question: what are symmetries of Gromov-Witten invariants? In C infinity case, what one has is the following: one has this group of diffeomorphisms of X. Consider a group of connected components. It's some huge countable group and contains stabilizer of component of the space of symplectic structures or tame almost complex structures. It's some countable set on which countable group acts. There is some stabilizer. It's not by zero of symplectic morphism for any symplectic form, I want to say. It's some certain group. And then this group, called it G, then G maps to automorphism of H2, or maybe if one more pedantic by 2. And here there's some kernel, and here there's the image. And for the kernel, kernel maps to automorphism of cohomology, and it takes a risky closure because the whole thing is formulated algebraically. So you get some kind of algebraic group and some discrete group. And you get semi-direct product of discrete group and algebraic group. This is a group of symmetries. And similarly, in algebraic situation, you get some discrete group, things which act on neurons Severi group, and then they get Mumford-Tate group, which is a different guy, but I don't know how it interacts with this. Yeah, so it looks at these two pictures, gives kind of things which can help to each other. They are not necessarily one contained in another, so there were two different restrictions. And another kind of big mystery, this whole story, if you have the spectrum should correspond to decomposition of Foucault category of your variety, to different elementary pieces. And now, what goes on? Suppose my variety is defined on a field of characteristic 0, but not Q, but something like, suppose my field is U, some square root of 2. It has two different embeddings to complex numbers, plus and minus square root of 2. And so if you get algebraic variety of this field, then I get two different symplectic manifolds. Foucault categories will be different, but parameter space are kind of the same. You cannot identify because basic homology are not cannot identify, but still kind of all the structure looks the same. It looks that Foucault categories have the same modular spaces. Are they equivalent or not? I have really no idea. But it's really a fascinating question.
But is there isomorphism between the non-commutative core structure?
Yes, but after extension of scalars, yeah. Okay.
All right. Let's thank Max. Question.
So on the infinity side, you had this decomposition of K theory.
Yes, yeah.
On the algebraic side, you had this semi-orthogonal decomposition of
Yes.
So do you expect that these two correspond to each other?
Yeah, because here I get projection functions which should given by kernel,
Yes.
and the class on K0 will be class K0 in.
Yes, but what I'm asking is, do you expect this one to be a finer decomposition than the one you get?
Of course, finer, because it's in a level of categories.
The image will be K theory.
If you consider the image of this projector in topological K0 will
One of
be.
the projectors of one of the pieces in the C infinity world, or could it be even smaller than that?
No. What I expect, I get for each point, I get an end effector which projector in retract your category to a smaller category, and it given by some kernel, and this kernel given some class on algebraic K0 square, and then it gives class on topological K0, and this gives a projector in topological side, which is finer story than just decomposition.
So if X has like X is Fano and has like a lambda Ginsburg model
Yes.
mirror, so then this like choosing a parameter is mirror to some kind of deforming the superpotential by some parameters.
Yeah. The story is a form. If you consider superpotential, which are kind of global, it's from only small part of Frobenius manifold. It will be some universal deformations.
So then this like in that case these pieces are kind of generically standard.
Yeah.
Is that do you expect that here as well? Like for generic choices of parameters, are these like there's always the same number of?
Of course, yeah. No. It's pure kind of algebraic geometry. If you get kind of analytic multivalued function, then outside of device it has the same number of branches. Yeah, it's just properties.
Small pieces always, like more pieces.
Yeah, there will be some elementary. I will talk more about these elementary pieces and the whole story.
I think generically they will be.
Sorry?
Generically they will be, right?
Only for Fanos at best.
Okay, yeah, Fanos. I mean, I don't know. I don't have the intuition about that.
So just to clarify, so you didn't make any assumptions with X, but I mean, X is a Calabi-Yau, there are no semi-orthogonal decompositions.
No, you just get 1 point. You have nothing. Yeah. For general
And then what will, I mean, your construction is very general, you didn't say.
Yes, nothing. No abstract.
So what will be?
It will be just 1 point. Yeah, for general type, Calabi-Yau will be no decomposition. Yeah, so it's really tied to minimal model problem, the story.
Other questions? If not, let's thank Max again.